Okay, good afternoon, everyone. So thank you for joining us for the fourth session in the machine learning seminar series that's sponsored by RI-CTR and the Data Science Initiative. Our format's a little bit different this time. We have two speakers, two students who will be talking about their work involving use of machine learning and deep learning. So we'll be starting with our first speaker, Ruotao Zhang, who's a PhD student in the Department of Biostatistics. Ruotao obtained a BSc in mathematics from Imperial College London and graduated from University of Oxford with an MSc in applied statistics. Today, he'll be talking with us about the role of calibration in uncertainty-based referral for deep learning, and I'll hand it over to Ruotao.
Thank you, Liz. Can everyone hear me fine? All right. So hello, everyone. Thanks for coming. Today, I'll be introducing one of my research projects that focuses on studying the role of model calibration in uncertainty-based referral for deep learning models. And this is joint work with my advisors, Dr. Stein-Grimson and Dr. Gatsonius. So I'll first talk a little bit about why we want to study this problem, the motivation, and also related research in the literature, and also what our work is focusing on. So, since 2012, when deep learning models showed their power in classifying natural images, they have been widely studied in medical image analysis, both for diagnosis and prediction tasks performed with many different imaging modalities, including CT, PET, MRI, and ultrasound. And there's a lot of work in different fields. Just to name a few, for example, in cardiovascular imaging, in neuroradiology and mammography, and so on. And the references that I'm giving here, they are all review type of papers that are summarizing current work and also pointing out many technical difficulties that need to be addressed, such as deep learning models. They usually require a lot of data for training, and in many cases, obtaining a large amount of high quality labeled images is just very expensive. There's also the problem of interpretability. There are also many studies that are looking at how robust the models are when applied to a population that is different than the one they were trained on. So in our paper, we focus on the problem of predictive uncertainty evaluation and also its relation to model calibration. Just to give you a very brief background, there has been a lot of research focusing on how we can obtain predictive uncertainty from a deep learning model. In other words, we not only want the point estimates of the probability of someone having, say, certain disease, but we'd also like to know how confident the model is about that prediction. So there are many different methods in the literature that we can use to get that kind of information. But what we are focusing on in our study is how we can evaluate those predictive uncertainty. In other words, we want to know how good those estimates are. And this is where this idea of uncertainty-based referral comes in. I'll talk more about this in later slides, but I want to first introduce how we measure model performance and how we get those uncertainty estimates that we want. Okay, so to evaluate performance of the prediction model, we basically use the following two metrics, the area under the ROC curve and the expected calibration error. So these two metrics, they are measuring very different aspects of the model. The AUC measures the ability of a model to discriminate between the two different classes. Here, we are assuming binary outcomes. So Y is either 0 or 1. And this R of X theta hat in equation 1 is just the predicted probability for observation X from the neural network model with parameters theta hat. And on the other hand, the ECE is measuring the calibration error, which tells you how closely the predicted probabilities reflect the true likelihood of something happening. So AUC and ECE, they're measures of model performance. they are not measures of how good the uncertainty estimates are. And I just want to mention this here because later on I will introduce two other metrics that are designed for evaluating uncertainty estimates. So essentially in total, we'll have 4 metrics, 2 for model performance, which are the AUC and ECE, and the other 2 for uncertainty estimates. So now I'll briefly go over how we actually obtain the uncertainty estimates. And after that, I'll introduce how we evaluate them. And that's where the other 2 metrics come in. Okay, so even though there are many different approaches in the literature for computing predictive uncertainty from neural networks, they can almost all be written in this form in equation 3. So the final prediction for a person with covariance X star, right, the predicted probability of this person having certain disease, is just the average of the predictions for this person from capital T different networks. So in other words, you somehow get T neural networks and you use them to make T predictions for this person and then take the average. And that gives you a single point estimate for this person. And once we have this, we use the entropy to measure the uncertainty associated with this prediction. So this is how we get the predictive uncertainty for each case. Now the problem is, how do we get T different neural networks? Because we need T different predictions for each person. So this is where different methods in the literature differ. I'm not going into the details of these methods, but I've listed the ones that are popular, and they're also the ones that we're using in our study. So these approaches, they all have different properties and connections to either frequentist or Bayesian ways of dealing with the problem. But for the purpose of this talk, you can just think of them as different ways that give you T network models and from which you can compute the predictive uncertainty. So now I'm going to introduce an important concept in our paper, namely uncertainty-based referral. And this is the tool that we use to evaluate uncertainty estimates. So imagine there's this automated diagnostic system that reads patients' image scans. And the way this system works is that if it's certain about a prediction, then it's going to output that prediction and move on to the next image. If it's uncertain about a prediction, then it's going to refer that case to human experts for further examination. So this is called uncertainty-based referral because cases with higher uncertainty are referred. So we can use a referral curve, which is given down at the bottom of the slides, to visually examine its effectiveness. So this referral curve, it plots the proportion of referred cases on the x-axis and model performance estimated using the remaining, essentially not referred cases on the y-axis. So for example, if 10% of the cases are referred, then this system would refer the 10% of cases that have the highest predictive uncertainty, and the corresponding y-coordinate on this curve would be the value of model AUC estimated using the remaining 90% of the observations that are not referred. So if uncertainty estimates are helpful for identifying hard to classify cases, then model performance should improve as more and more cases with high uncertainty are referred, right? Because the model is only keeping the cases that it's certain about, which means the referral curve should be increasing. So in order to quantitatively measure the trend in those referral curves, we propose the following 2 metrics. So these are the 2 metrics that I was talking about. So they are designed for measuring the performance of uncertainty estimates. So the first metric is the Mankando statistic that estimates how monotonic a trend is. And the MK statistic, it is bounded between -1 and 1. with higher values reflecting a more increasing trend. So it's equal to 1 for strictly increasing curves, and it's equal to -1 if we have a strictly decreasing curve. The second metric is the area ratio statistic, the AR statistic, as illustrated in this figure here. So in order to calculate AR, we first compute the difference between the area under the referral curve and the area under a random referral strategy. So that's the area defined by the dashed line. And then we compute the area of maximum improvement that any referral strategy can have. That's the area defined by the dotted lines. So the AR statistic is defined as the ratio of this dashed area to the dotted area. And the AR metric, it can range from -infinity to 1. So when it's positive, it means uncertainty-based referral is more effective than random referral. If it's negative, then it means the current referral strategy is not even good as good as the random referral. So just to summarize, we now have 4 metrics, right? We have AUC and ECE for measuring model performance. We have MK and AR for measuring performance of uncertainty estimates. And now I'm going to present the analysis that we did using data from diabetic retinopathy detection. So in other words, we want to apply those uncertainty estimation techniques and see how they perform under various configurations. So we used public available imaging data from the diabetic retinopathy detection task, and we refer to it as the DRD dataset. It consists of high resolution retina images, each with an integer outcome measuring the severity of DR. And here we defined a binary outcome with 0 being no DR or mild DR, and 1 if the patients have moderate, severe, or proliferative DR. So there are around like 35,000 training images and 53,000 test images in this DRD dataset. And the training and the test images, they're independent in the sense that they come from different patients. We also randomly selected a subset of the training data as a validation data set. So the final training validations test split is given here. We also used the second data set called the Aptos 2019 to evaluate the performance of our model under external validation. So it consists of around 3,600 images. And essentially the deep neural networks that we train and also the uncertainty estimates that we fit are using the DRD training set, and they are then evaluated on the DRD and Aptos test data sets. For the experiments, we used 4 pre-trained networks with increasing complexity. So the number in the parentheses, they are the number of parameters in the neural network. And here we have 2 ShuffleNet V2 networks with different number of output channels. And we have the MobileNet V2 and also the ResNet 50. And we're using the following 4 uncertainty estimation methods to compute predictive uncertainty from those networks. So essentially there were 4 by 4, a total of 16 combinations here. And the results are given in this table. So again, we have the 4 methods for estimating uncertainty combined with 4 different type of neural networks. And we are using AUC and ECE for evaluating model performance, and MK and AR for evaluating uncertainty estimates. So down at the bottom of this slide, we've listed the 4 metrics, and the arrow in the parentheses just indicates whether it's higher the better or it's lower the better. So for example, for the MK metric, it takes values between -1 and 1, and we want it to be large. And also for the AR metric, it takes values between -infinity and 1, and we also want it to be large. So as we can see from this table that nearly all models, they have reasonably good performance in terms of AUC on both test data sets. And the performance is generally better for the more complex models, the ones that have more parameters. However, if we look at the uncertainty estimates, overall, there's none of the methods for uncertainty estimation consistently outperform the other ones. So they all have different levels of calibration error with, usually higher ECE on the Aptos test data set than on the DRD test data set. And the performance of uncertainty-based referral, which are measured by MK and AR, they also varied across both data sets. And in certain cases, they were often worse than random referral, right, which are indicated by those cases with negative AR or negative MK. So for example, if we look at this one, the deep ensemble of ResNet 50, right, sort of shows promising results for uncertainty-based referral on the DRD test data set because it has MK of 0.82 and also an AR of 0.1. However, if we use the same model to flag images in the Aptos test data set, as we refer more and more uncertain images, it will result in worse and worse AUC, which is reflected in those negative values here, right? Because we have -0.94 and the -0.94 and -0.14 for the Aptos data set. So if we look at the referral curve in this case, which is the figure on the left, we can see clearly that as we refer more and more cases, the model AUC keeps going down. And if we go back to this table again, and we see that this kind of undesirable behavior actually occurs for many models, right? Even for the ones that generalize well in terms of AUC to the external validation test data set, to the Aptos test data set. So in other words, although it appears that the model generalizes under external validation, the uncertainty estimates do not generalize. And next we look at how model calibration affects the uncertainty estimates. Right here we are plotting ECE against AR and MK for all the experiments that we conducted, and it's clear that there are this negative correlation between ECE and AR and also between ECE and MK. So this high negative correlation supports our hypothesis that lower calibration error, so that's lower ECE, is associated with more effective uncertainty-based referral. So that's higher AR and MK. And now if we go back to the figure on the right, this is the calibration plot, which shows that the network is systematically overestimating the fraction of observed cases, right? So this is indicated by this calibration curve falling below the diagonal. So from this, we see that for those cases, so for those cases that the model predicts a 0.5 probability of being positive, so that's the ones here, only 20% of them, right? Only 20% of them are actually positive cases. So hence the predicted probabilities from the model fail to identify the most hard to classify cases, right? On the other hand, if we look at the cases where the model predicts a 0.8 probability of being positive, around 50% of those cases are positives. This means these are the observations that the uncertainty-based referral should be targeting because these cases are equally likely to be either positive or negative. However, this subset of interest is not being prioritized for referral since the model predicted probabilities systematically overestimate the true probabilities. And this is why bad calibration affects uncertainty estimates. So that discussion suggests, calibrating the models could improve the effectiveness of uncertainty-based referral. So next, we tried a popular calibration technique called Pratt scaling, and we applied it to all the experiments. And this figure shows the density plots of the MK and AR statistics across all the experiments when the models used no post-calibration, so that's the dashed lines, and also when the models used the Pratt scaling, so that's the solid lines. So it's clear that Pratt scaling is improving both the AR and MK metrics as they tend to have higher values after calibration. So this gives us this is giving us empirical evidence that calibrating the models will help with uncertainty estimation. So to wrap up my talk today, I've summarized a few key takeaway points from our study. So first, none of the uncertainty estimation methods is guaranteed to produce robust and consistent uncertainty estimates. And in many cases, we see that the model is generalizing well to the external data set in terms of AUC, but it does not mean that the uncertainty estimates also generalize. And we also identified a strong relationship between model calibration and how effective uncertainty-based referral is. And we presented evidence that post-calibrating the models can improve the uncertainty estimates. And lastly, I didn't include this in the slides, but we were able to prove that if instead of the AUC, if we use the classification accuracy as the measure for model performance, then a well-calibrated prediction model will always produce an increasing referral curve. So in other words, if we have a calibrated model, as we refer more and more uncertain cases, the classification accuracy evaluated on the remaining cases will always improve. So we were able to prove that theoretically. And this concludes my talk today. Thank you for listening, and I'm happy to take any questions.
Great, thank you so much. Are there any questions? If anyone has a question for the speaker, you can put them in our chat and I'll read it out for Ruotao. I guess maybe while we're waiting for maybe people are typing. I mean, I think you did a great job kind of talking about the different metrics and then kind of showing it, using it in a study. Do you have some thoughts to kind of next steps that you might take based on what you've done in your work, and just other ways you might be able to apply what you've done so far?
Yeah, we are, because this study shows how calibration is related to uncertainty estimates. We are thinking of how we can sort of train a model that is automatically calibrated in the population that we are interested in. So, because current methods, they're always, at least most of the current methods, they're always using like this technique called post-calibration. So which means you first train a model, and then you get a separate validation data set and use that separate validation data set to calibrate your model. So that's called post-calibrating because it's after the training is done. So what we are thinking is we are looking at different ways to see if we can incorporate that process into the training. So essentially you just have one whole procedure, and after training, you have a good model in terms of both AUC and also calibration. So that's some of the stuff that we're looking at. Yeah.
Great, thank you. I think we have a comment, great talk. Any others? I could ask another one, but I'll see if anyone else has a question. And I guess another one, just thinking about people maybe who are, thinking about our audience, some maybe those doing deep learning and some maybe interested in it. I guess one question is, could you maybe talk a little bit about the programming languages you're using, kind of the computing environment you're using to do your work, just for those who maybe just wanting to know, how do you get started? And any advice you might give from kind of someone who's interested in this from a training, what do you need to know? What do you need to learn? And, in terms of programming languages or other things like that?
Mm-hmm. Yeah, for this study, I used actually, because in terms of deep learning models, there are essentially just two main programming languages that you can use is either TensorFlow or PyTorch. So I've actually used both of them in the study because they all have their own pros and cons in terms of how you code and how you deploy the model. Personally, I think if I started with TensorFlow, but it's not as flexible as PyTorch. But I think a lot of people in the industry, they use TensorFlow. I think it's because it's easier to deploy in the production system. But I think for academia purposes, it's easier to use PyTorch because it's easier to experiment different things. It's more flexible. So that's essentially what I have my own experience in using these deep learning frameworks.
Great. Yeah, that's really helpful. And you actually have two questions have come in. So the first, do differences in prevalence of disease in training set versus validation set impact the analysis you were describing? If so, how do you deal with that?
Yeah, I think in our data sets, the prevalence rate is not that a big deal because I didn't really mention this in the slides, but when we trained the models, we did use different weights for different samples in order to adjust for the different prevalence rate in these two different data populations. But in our case, it's not really that big of a problem. But I do think if the problem that you're looking at, the two data sets or the two populations have vastly different prevalence rates, then it could be a problem in terms of how you estimate the uncertainty estimates and how you do calibration. Because if the target population that you are interested in has a very different prevalence rate, then the model that you trained using your source population might not be transferable to that new population. But again, that's a different problem that people are trying to solve. Yeah.
Great. Okay. And I think last question. So from someone who came late, so might have missed it, but is asking, what is the difference between post-model calibration and hyperparameter tuning using a validation set?
Oh, we are using the validation set to do post-calibration. And for the hyperparameter tuning of the neural networks, we didn't really use that validation set. We used the cross-validation of the training set. So essentially, we use the training set for training, and that includes the hyperparameter tuning. And once that's done, we use the validation sets for post-calibrating. Does that make sense?
Yep, they said thank you. Okay, I think perfect timing. Thank you so much for a great talk and for those great responses to questions. I think we'll now transition to our second speaker. Yep, slides look good. There we go. Okay, great. So I'm happy to introduce Dilum Aluthge. He is an MD, PhD student in the Brown Center for Biomedical Informatics, Center for Computational Molecular Biology in the Warren Alpert Medical School. Dilum earned his Bachelor of Science in Applied Mathematics at Brown and is the co-creator of the PredictMD machine learning framework that's implemented in the Julia programming language. Dilum will be talking with us about supervised machine learning workflows for electronic health records. And I'll hand it over to Dilum to tell us a little bit about that topic.
All right. Is my audio sound good?
Yep, sounds good.
Perfect. Okay, so I'm Dilum. I'm an MD PhD student here at Brown. So I'll be presenting a high-level overview of supervised machine learning and what that workflow might look like if you're working with healthcare data in a clinical setting. For example, if it's coming from a source like an electronic health record, and how you might go from a machine learning idea all the way through training your model and then ultimately integrating back into that electronic health record in a way that's clinically useful. So my disclosures, I'm a consultant at Pumas AI. So I just want to define a few terms that I'll use repeatedly throughout the talk. A GLM is a generalized linear model. It's a type of supervised machine learning model. If you've heard of a linear regression or a logistic regression, those are types of a GLM. An EHR is an electronic health record. So examples of those are Epic and Cerner. And HIE is a health information exchange. So example of this is Current Care from the Rhode Island Quality Institute, which pools and consolidates all the healthcare data for all patients in Rhode Island. And HIS is a health information system. So things like EHRs and HIEs are examples of a health information system. And a CDS is a clinical decision support. So these are the 5 stages that we'll talk about during the talk. Once we've gone through these 5 stages, I'll present an example problem based on electronic health records, and I'll show how that fits into these 5 stages. So the 5 stages are: define your machine learning question, train your machine learning model, internal validation of the model, and internal validation I'll use synonymously with cross-validation, external validation of the model, and integration of the model into a health information system, such as an EHR or an HIE, in the form of a clinical decision support tool or a CDS tool. So we'll start with defining the machine learning question. And the very first decision you have to make is what your features and what your labels are. Your features are what goes into the machine learning model as inputs. They're the data that your model will use when it makes a prediction. Your labels, or you'll hear sometimes people call these the target. This is what you're trying to predict. So sometimes you know what your labels are and sometimes you don't. And this is the distinction between supervised and unsupervised machine learning. So in supervised machine learning, you know that you have something you're trying to predict. So for example, maybe if you're trying to predict mortality in ICU patients, the label that you're trying to predict is mortality. And then your features might include things like demographics, vital signs, medical history, comorbidities, other risk factors that go as inputs into the model. Or if you have a population of diabetic patients and you want to predict HbA1c, now your label or your target is HbA1c. Sometimes you don't have a target that you're trying to predict. You just want to know if there are, say, clinically relevant clusters or subgroups. And that's when you use something like unsupervised machine learning. There's no label. You just want to uncover if there's a hidden structure within your population. So this shows the breakdown of machine learning into supervised or unsupervised machine learning. And supervised machine learning breaks down into classification or regression, which is the next distinction we'll make. So in classification models, there's a finite number of categories into which your label can fall. If there's exactly 2 classes, we call this binary classification. A good example is mortality. Either a patient is alive or they're deceased. The alternative, if you have 3 or more classes, is multi-class classification, in which you have 3 or more classes. So one example might be destination after being discharged from the hospital. The patient can go home, they can go to short-term care, long-term care, maybe they're deceased. There could be other additions to this list as well, besides those just 4. Cancer grading and staging is another example where there are 3 or more classes that your patient could fall into. In contrast, if you don't have a number of classes or categories, and there's not a finite number of values, we call this regression. And intuitively, a regression model is where your label can just take on any real number. So anything like HbA1c, systolic blood pressure, creatinine clearance, these don't have categories or boxes. They can be any number within the range. So this illustrates the difference between regression being kind of a real number and classification being a discrete set of classes or categories. And this illustrates, again, that you can have binary classification with exactly 2 classes. Anything else is called multi-class classification. So I want to present just the names of some supervised machine learning models. I don't want to get into the details of how they work specifically, but these 4 I think are very good starting points if you're trying to decide what models to start off with for your problem. So like I mentioned, you have generalized linear models or GLMs, you have random forests, you have support vector machines or SVM, and you have artificial neural networks, as was discussed in the previous talk. All 4 of these are suitable for binary classification, multi-class classification, and regression. A GLM goes by different names based on the problem. Sometimes it's called a logistic regression, sometimes it's called a linear regression. These are all examples of the same model, it's just based on what type of problem you're trying to do. One thing that's not on this slide that was also highlighted in Ruotao's previous talk is that if you're working with imaging data specifically, so maybe you have data from, like he mentioned, ophthalmology or radiology, dermatology, maybe pathology or histopathology, or histology. Those are all cases where artificial neural networks are the state of the art. For imaging data, you really want to use artificial neural networks. Anything else is not going to give you as good of a result. So now that we've talked about defining the question, let's get into how you train your model. So this is the procedure for training a model. So you select one or more models that you're going to train and compare. This may be one or more rows from that table on the previous slide. You randomly shuffle your data set, and then you randomly split it into the training set and the testing set. For example, you may choose a 70-30 split. You train each model on the training set, and then you evaluate it on the testing set to see the performance of the model using some of these metrics. So good metrics include sensitivity and specificity. Sensitivity tells you how likely it is that you'll avoid the type 2 error, where specificity is about minimizing type 1 error. A high sensitivity, because it minimizes type 2 error, is very good for ruling out a condition, whereas a high specificity, minimizing type 1 error, is good for ruling in a condition or confirming a diagnosis. You can also plot receiver operating characteristic curves, or ROC curves, and you can look at the area under the ROC curve, the AUC or the AUROC. And then you compare the models, and what you really want to consider is the clinical context. Are you trying to make a good screening tool, in which case you want to prioritize sensitivity? Or are you trying to confirm maybe another diagnosis that has come from somewhere else? And that might be where you want to prioritize specificity. So these metrics can't be considered in a vacuum. You have to put them in the clinical context. So once you've trained your model, you can now internally validate it. And I use the terms internal validation as a synonym for cross-validation, which I use synonymously with k-fold cross-validation for some number k. So internal validation or cross-validation is performed using the original data set that you trained your model with. So this is the training set. It evaluates how robust your model is. And the steps are: you take your original training data set, you split it into some k subsets. So if k is 10 and you're doing 10-fold cross-validation, you split it into 10 subsets. And then in each iteration, the kth subset is held out for testing, and all the other subsets are combined together for training. It's kind of hard to visualize. This is what it would look like visually. In iteration 3, for example, the third subset is held out for testing. So all the other, in this case, 4 data sets would be combined for training. You train on that, and then you evaluate the AUROC on this third held out test set. So internal validation is really important. And once you've completed it, you're not done. Now you need to do what we call external validation of the model. So remember that internal validation showed how robust our model training policy is and how robust our model process was. External validation is different. It shows that our model is generalizable, and importantly, it's reproducible. So this is where you show that your model is reproducibility. During internal validation, we use the original training set. But for external validation, it has to be a different data set. And you don't train your model, you just only test it on this new data set. So if you trained on patients at Rhode Island Hospital, maybe your external validation set, you take patients from a hospital in California. If you train on ICU patients at Rhode Island Hospital, your new data set might be hospital floor patients at Rhode Island, right? So it's the same hospital, but we know that ICU patients are very, very different in physiology than hospital floor patients. So if you show that your model is trained in ICU patients, but it still has good predictive performance on floor patients, then you're showing that you're able to capture something that's real and relevant to the clinical context and isn't overfitting to the particularities of being in the ICU. You can also do a time-based way of breaking down external and internal validation. So one option is that you have the same hospital, but you train on an earlier data set, 2005 to 2010, and you test on a new data set that's the same hospital, but it's maybe 2010 to 2015. So again, showing that you're performance is good even when it's trained on new years of data show that you're not picking up again on something that's specific or overfit to your original years, but you have something that's more reproducible. So these three are just examples of external validation. There are, I mean, countless other examples. The key is that you really do want these to be two independent data sets. So for example, if you look at the second row, if I trained on ICU patients at Rhode Island Hospital, and then my new data set was all Rhode Island Hospital patients, I wouldn't consider that to be a good form of external validation, because the new data set, the quote unquote external validation set, would actually include patients from the original training set. So if that makes sense, you want your two data sets to be disjoint and independent. Otherwise, you can't really say you've done external validation. All right. So the first 4 phases of this workflow are all about training and validating your machine learning model. But once you're done with the machine learning process, you're not actually done with the full workflow. What you want to do is to go back to the health information systems that are of interest. Maybe it's an EHR, maybe it's an HIE, maybe it's multiple health information systems. And you want to integrate your model back into the system in the form of a clinical decision support tool, or a CDS tool. And the way that we integrate models into health information systems is by using open standards. So several decades ago, this was not the case. If you wanted to integrate into a health information system, you were often stuck using proprietary vendor-specific APIs. So if you wanted to interface with the Epic EHR, you'd have to use Epic's own proprietary technology. And then when you want to go and integrate with Cerner, you have to use Cerner's proprietary interface. But fortunately, today, the state of the art is to use open standards that allow your app to use the same interface to integrate with multiple health information systems. So this makes your application much more portable and increases the chance that your app will be available in multiple healthcare systems, in multiple states, in multiple countries, and in multiple clinical settings of interest. There are 3 main standards I want to emphasize: SMART, also known as Smart on Fire, FHIR, and USCDI. So SMART, or Smart on Fire apps, this is the open standard for authenticating an application to a health information system. So you have to authenticate that the user has the right to see protected health information. Maybe they're a clinician taking care of a patient. Maybe they're the patient themselves logging into their online patient portal. Maybe they're a patient's family member. So you need to make sure that the person has the appropriate permissions, and this is done with an open standard called Smart on Fire applications. Once you've authenticated, you need to read the data from the health information system so that you can put it as inputs into your machine learning model, right? So the main way to read data is an open standard called FHIR, which stands for Fast Healthcare Interoperability Resources. So it's spelled FHIR, but it's pronounced FHIR. And this is the gold standard for reading data out of an EHR or an HIE or another health information system. And then when you get those data, you'd like those data to be in a standardized format, right? You don't want every different EHR using its own code for vancomycin, right? There should be a standardized way of talking about vancomycin and vancomycin related information. And the gold standard for this is called the USCDI, or the United States Core Data for Interoperability. These are federal standards for a selected set of healthcare data fields. And they're provided by the Office of the National Coordinator for Health Information Technology. So you use FHIR and USCDI, you get the information your machine learning model needs, and then you put it into the machine learning model. You get the predictions, maybe you get a probability. And as Ruotao mentioned, maybe you don't also get a probability or some classification, you also get how uncertain you are about that estimate. And based off of these results, you present a recommendation back to the user that can be used in a clinical context. So these are the 5 stages of the workflow. We have a little bit of time left, so I want to now present an example use case, or an example, a hypothetical example of a machine learning model and how it might fit into this workflow. It's actually not completely hypothetical. This is actually a problem that I'm actively working on currently. So the problem statement here is, automated or semi-automated curation of the problem list. So, as clinicians, I think we intuitively understand that an inaccurate or incomplete or outdated problem list can lead to suboptimal clinical care. I think this is intuitively clear to all of us as clinicians, but I want to give a particular specific example. Suppose that you're seeing a patient, maybe you're seeing this patient for the first time. Maybe it's one of your colleagues' patients and you're seeing them for the first time. And what we like to do is we like to review the patient's chart in the EHR in advance of seeing the patient so we can prepare for the visit ahead of time. You may only have 15 or 20 minutes for your patient visit, so you want to prepare in advance if there are things that you need to talk about, that you don't want to leave the patient's room without covering X, Y, and Z. For example, for diabetic patients, every year there's certain screenings and preventative care that you need to take care of for your primary care patients that have diabetes. You need to make sure they get their annual eye exam, their annual foot exam, the annual labs and screening that need to be done for patients with diabetes because of the risk factors that they have. But if the problem list in the EHR doesn't list diabetes, then you might not know in advance to prepare all of those referrals and screenings and tasks. You'll find out when you get into the patient's room, right? It will get done, but the visit might be less efficient than if you'd been able to prepare in advance. So what we want is to have a complete and accurate and up-to-date problem list. But how do we do this? Well, one option is to take information from the medication list, for example, from various pharmacies, and use this to automatically make suggestions about additions, deletions, and modifications for the problem list. Just as a very simple example, if you look at a patient's pharmacy data and they're regularly filling a prescription for metformin, and there's nothing else on the problem list for which metformin would be an indication, there's a very high probability that diabetes should be added to the patient's problem list. Now, it's not 100%, right? You can't make that guarantee 100%, but there's a high probability that you should ask the patient, do you have diabetes? Should this be added to your problem list? So can we build a machine learning model to learn these information and turn that into a support tool? So here are again the 5 steps of our machine learning workflow. Define the machine learning question, train the machine learning model, internal validation, which is cross-validation, external validation, and integrate the model into a health information system. So let's go through these 5 steps. Define the machine learning question. Can we use medications to predict the probability that a patient has some problem? And I'll make it even simpler. Let's focus first on a single problem on the problem list, diabetes. Can we use medications to predict the probability that a patient has diabetes? So your features in this case are all the medications and whether or not a patient is taking them. Your label is a binary classification label, right? It's diabetes. Yes, they should have diabetes on the list. No, they shouldn't. This is supervised machine learning because we have a label. And like I said, it's a classification problem because there's a finite set of categories, and it's binary because there are only 2. And some models I would consider, for this case, I would consider training and comparing all 4 of the machine learning models I talked about previously. I would take a GLM, in this case, a logistic regression, a random forest, a support vector machine, and an artificial neural network. And I would probably look at sensitivity, specificity, and AUROC as my metrics. And I would compare the 4 models and evaluate how they perform. And then for internal validation, suppose my training set. So suppose in step 2, my training set was all primary care patients seen at Brown Medicine from 2010 to 2015. If that was my training set from step 2, then that's what I use as my internal validation set for step 3. I use the training set, which hypothetically, again, this is a purely hypothetical example. We take all primary care patients from Brown Medicine during this time period. And then maybe for external validation, we have research collaborators and partners in a different state, in Kaiser Permanente's healthcare system, perhaps. And we can take all of their primary care patients, maybe from the same period of time, maybe from a different period of time. And then once we've externally validated, how would we integrate this model into the health information system as a clinical decision support tool? One option, like I mentioned with the previous standards, is to use the open Smart on Fire application standards to integrate into an EHR. Maybe I integrate into Epic or Cerner or eClinicalWorks or whatever my clinical practice uses, and makes suggestions if a patient has a high probability of having diabetes, but diabetes isn't already on the problem list. And this last part is tricky because you want to make suggestions to the right person at the right time, right? So you want to identify who's the correct clinician and what's an appropriate way, an appropriate time to make that suggestion. You don't want to, put a pop-up in the middle of someone's EHR, certainly. That's almost never a good idea. And you don't want to interrupt someone's workflow when they're doing something else. So identify, well, what's the right time to suggest to someone to update the problem list? And then find a non-intrusive and helpful way to make that suggestion. All right, so that's the end of my example. So I see we have some time at the end for questions. Also, you can feel free, Liz, before Liz gets into the questions, feel free to email me. I'll leave my email address up for a few seconds. I'm happy to answer any questions about the presentation or just talk more about machine learning, again, in a clinical context, which is near and dear to my heart.
Dilum, thank you so much. I think that was great, kind of the overview of the workflow, and then kind of thinking about, helping us think about how do you actually put models into practice, and then kind of highlighting an example. You actually have a few questions. So I think the first one is kind of a mix of comments and questions, but I think a really good one. So I'll pretty much just read it so you have all the details, but really this is related to the EPIC sepsis prediction model that many of us on this call may have already heard about. But the question, so an important recent JAMA publication presented the result of a study externally validating the EPIC sepsis prediction model, log regression model created by EPIC using data from over 400,000 patients across 3 medical centers. The model did terribly, highlighting the importance of local validation before clinical application. Machine learning models are more complex. How will hospitals, especially community hospitals, be able to validate these models? Who bears the responsibility of doing the external validation? The EPIC sepsis prediction model is available and probably used by a majority of medical centers that use EPIC, the largest EHR vendor, and EPIC's model is proprietary. They never publish their model or derivation and validation data, and bypasses the peer review process.
This is near and dear, as Liz mentioned, Dr. Abbasi, this is near and dear to many of our hearts. It illustrates something, I think, for the clinicians on the call, that you've known. You didn't need this paper to know this. I was talking with a very good friend of mine who's a radiologist, that he recently completed his intern year in general surgery, and so he was using EPIC a lot, and yet was using this model a lot. And he's like, very anecdotally, what he hears from his colleagues is that the model often flags a patient as having sepsis when they don't really have sepsis, and fails to flag patients that have sepsis, but doesn't provide a notification. And yeah, the JAMA publication showed that the AURC is in the 60% and is below what any of us would consider for clinical practice. So who bears the validation for this? So I maybe this is I'm speaking only, this is opinion only, right? So this is just my personal opinion. I would say that most, if not all, of the responsibility for validating a model comes on the machine learning practitioners as we develop and train those models. So in this case, I would say that EPIC, having created and promoted this model, should have externally validated it and published those results. Now, the trick about EPIC, or any situation in which the EHR vendor is also the machine learning model vendor, is that, like you said, they have the ability to bypass the review process. They can just deploy it and say, here it is, because they control the platform. For those of us that don't run the EHR, we do not have that luxury. And so I think you will see, hopefully, that people that aren't the EHR vendor that are developing machine learning models, I hope that they will be taking on the responsibility of doing the internal validation and the external validation. I think if you want to make the pitch to a hospital or a doctor's office or a clinical or healthcare system to implement a model, I think you have the responsibility of bringing those data with you. Especially, you mentioned, especially community hospitals that might be a smaller system or a standalone hospital. I don't think it's feasible to expect them to take on all of the work and the cost of validating by themselves. Now, one alternative, so I've suggested that the machine learning practitioner should do this. An alternative model is that you partner with a healthcare system. So maybe I me and my group develop a model, and we do internal validation, maybe a retrospective analysis, and then we partner with Lifespan, or we partner with Care New England, or we partner with the healthcare system, and we validate it together, and each side can bear some of the responsibility of the cost. But the current situation where all of the weight is put on every hospital that actually uses the system, and the creator of the system never actually validates it, I don't think that's the feasible long-term solution.
Great. Okay, we have two more questions. So kind of in relation to the previous talk, can you comment on model calibration that should be done prior to integration in a health information system?
Yeah, that's a great point. And I think you have to check that as part of the internal and external validation, right? So if you use your cross-validation to check the internal robustness, what I would do is, instead of taking your entire original data set and splitting it up into k-folds, first take a holdout of that, do cross-validation on some part of it, and do your calibration cross-validation on the remaining. An alternative, which is much more computationally expensive, is something called nested cross-validation. So you have an outer and an inner cross-validation. And the inner, essentially, is a for loop in a programming language. The inner loop would be done for calibration. The outer loop would be done for the normal internal validation. Now, this is much more computationally expensive, but it's very robust, and the results are very convincing. So that's how I would. And you can use nested cross-validation to combine something like internal validation and model calibration. And then on your external validation stage, I would also check your calibration. So in addition to, so say train at Rhode Island Hospital, I'm validating externally at Kaiser. When you externally validate at Kaiser, also use the metrics that Ruotao talked about to check your calibration. And if your model has a great AUROC on Kaiser, but the calibration metrics that Ruotao talked about are poor on your Kaiser dataset, I would be hesitant to proceed to integration until you've gone back and maybe improve your calibration in some sense. So I would definitely check all of those throughout the process as you get into the final steps before you integrate.
Great. And I think we have time for just one more question, and then we'll wrap it up. So it says, thank you for a wonderful talk. What would be your recommendations for applying this workflow to data sets that include repeated observations on the same individuals? For example, where observations are nested within individuals. I'm aware that data splitting can take into account this grouping. Is this sufficient, or should additional measures be considered? Yeah,
so this is a great question. If you randomly partition your data, but there are multiple observations within individuals, say patient X might have some observations in the training set and some in the testing set. So like you say, when you do the splitting, you can teach, whether you're doing just a regular 70-30 split or the k-fold cross-validation, you can teach the algorithm, whatever programming language you use, you can, like you mentioned, Andrew, you can teach them to group all individuals together. So you would actually split, you wouldn't split observations, you'd split patients. So 70% of patients, 30% of patients, and all the observations for a single patient are taken together. That's usually sufficient. It's worth noting that the external, if you make a mistake, external validation will catch this, because external validation should be different individuals, right? Seen in a different state or a different period of time or a different unit. So that should be helpful for catching that. I'll briefly mention that there are also machine learning models that can explicitly take knowledge about this clustering. The obvious example is a generalized mixed model or a generalized linear mixed model, where you can actually put information about these clusters or nesting or grouping into the model itself. That's a different approach to go. That's another valid way of doing these things. But I also think that it's sufficient if you don't want to use one of those models, a mixed model of some kind. It is sufficient to make sure that your data splitting correctly splits those patients. But you should check that you're doing that correctly. And external validation is one of those ways, because the populations are different, that you'll catch yourself. If you make a mistake and your external validation is really low, you'll say, oh, maybe I didn't do my splitting correctly. So it can be an extra guardrail or an extra warning flag that you might have done something wrong.
Great, thank you so much. I think we're at time. So thank you so much to Ruotao and Dilum for their great talks. Hopefully they were informative. I think they provided their contact information, so feel free to reach out to them. Thank you all for attending. And we have one more talk. I think that's next Wednesday. Dr. Joe Hogan will be presenting and closing out our series. So we hope to see you there. And the recording will be posted. Oh, there's the fall schedule. Yep. So Dr. Hogan will be talking about the role of machine learning in predictive and causal inference. So that'll close out our series. Everything will be posted. All the recordings will be posted. So you'll be able to watch them or refer others to them. So thank you again. Enjoy the rest of the night, and we'll hopefully see you next week. Take care, everyone.